Welcome to the deep dive. We're really glad you're here with us today because we're tackling something that I think everyone has dealt with recently. Just last week, actually, I asked my phone's AI for a really simple baked chicken recipe.
Oh, no. Let me guess.
Yeah, you already know. I figured, it would give me some oven temperatures, maybe a quick spice rub. Instead, and I'm not kidding, 5 prompts later, it was feeding me this massive philosophical essay on why chickens cross the road,
Of course it was.
completely forgetting that I was standing in my kitchen, literally holding raw poultry. It entirely lost the plot. And if you've spent any time at all interacting with modern AI systems, you've probably experienced something exactly like this.
Oh, absolutely.
Sometimes they are brilliantly helpful, right?
Yeah.
And other times they just spin out into these vague, rambling runaway states where you're like, how did we even get here?
It's arguably one of the most frustrating bottlenecks in modern tech right now. I mean, we have these massive, incredibly powerful language models, but keeping them on track during an interactive back and forth session, it's incredibly difficult. They just want to hallucinate.
Which brings us to the sources we're looking at today. We are exploring a truly groundbreaking specification document called Explicit Prompt Spec V1. And the mission of this deep dive is to unpack how a brand new programming language, which is called Explicit Prompt, is attempting to solve this exact problem.
And it's doing it in a really unconventional way.
Very unconventional. As always, I'm here as your resident tech analyst trying to figure out if this is actually practical for us to use. And you're here as our specialist in natural language programming to, well, keep us grounded in the actual architecture.
I will do my best.
So let's start with the basics, because this document throws around an equation of acronyms literally right out of the gate.
Okay.
Let's unpack this. It says the foundation is NLP1 plus NLP2 equals NLP3. Can you just break that down for the listener?
I'd be happy to. So if you're in tech, you're probably already very familiar with that middle term, right? NLP2.
Right.
That stands for natural language processing. That is the computational machine-driven side of things. It's how a computer analyzes a sentence, breaks down the grammar, tokenizes the words, and figures out the underlying data structure of what you actually typed.
The cold, hard math behind language.
Exactly. It's the classic machine learning stuff we hear about all the time.
But I have to admit, the first term, NLP1, that completely threw me for a loop.
Yeah, that's because NLP-1 isn't really a computer science term at all. It stands for neuro-linguistic programming.
Right.
It's a psychological approach that was developed back in the 1970s, and it's focused entirely on human communication patterns. It's about sensory cues, body language, tone of voice, and specifically how we build rapport with one another.
Wait, hold on, though. Isn't NLP1 sometimes associated with, like, self-help seminars or those high-pressure sales tactics? I mean, we're talking about matching someone's breathing patterns and mirroring their posture. How does any of that fit into programming an AI?
It's a fair point to be skeptical, totally, but in this context, we're looking at the core mechanics of rapport, stripped of all the seminar stuff.
Okay.
Think about it this way. When a therapist matches the pacing of your speech to make you feel heard, or a negotiator uses specific phrasing to de-escalate a tense situation, they are using NLP-1 techniques. It's highly organic. It's entirely focused on human perception.
Oh, I see.
So explicit prompt is looking at how to take those effective communication structures, how humans naturally build trust and clarity and formalize them into code.
Okay, so we have NLP1, which is human psychology and rapport,
Yeah.
and NLP2, which is machine processing and tokenization.
Right.
I assume NLP3 is the mashup of the two.
Precisely. NLP-3 stands for natural language programming. It's the synthesis. It's the attempt to program machines using English-like sentences, but doing so in a way that incorporates that human psychological rapport building right alongside the computational heavy lifting.
That's ambitious.
Very. But it's important to note here that explicit prompt isn't trying to be the entirety of NLP-3.
Right, the spec actually mentions it's a specialized minimalist subset.
Exactly. NLP-3 is a massive concept. Explicit prompt narrows that scope way. It's designed specifically for pre-processing user inputs in interactive AI systems.
Like catching the prompt before the AI sees it.
Yes, think of text-based AI games or highly structured chatbots. It acts as a filter. Before the AI even tries to generate a response about a chicken crossing the road, explicit prompt catches what you typed, forces it into a strict, unambiguous format, and applies those psychological pacing techniques so the system doesn't get confused.
It's a fascinating pivot, honestly. We spent all this time trying to make AI more complex, and explicit prompt's solution is to actually make it more rigid before it even gets a chance to speak.
That's the beauty of it.
And the retro inspiration here is just wild to me. Despite being this cutting-edge tool for modern AI, explicit prompt is modeled after early Forth-like kernels. We're talking about programming concepts from the 1970s.
It is brilliant in its simplicity, really. The architecture is incredibly lean. It operates using something called a kernel, spelled with an A, which is essentially the core runtime environment.
And how big is this kernel?
In explicit prompt, this kernel is tiny. We're talking about maybe 100 lines of Python-like pseudocode.
Wow.
Yeah. It's just enough logic to manage basic operations and absolutely nothing more.
Just 100 lines. That's practically unheard of today, right? Where every single app on my phone feels bloated with gigabytes of code.
Exact.
And alongside this tiny kernel, the spec talks about the dictionary.
Yeah, so the dictionary is where the actual vocabulary of the language lives. It's a collection of defined words that the kernel actually knows how to execute, and it's completely extensible. You start with a few basic primitives, and you can add to the dictionary as you build out your specific application.
So to write this code, to actually use these words from the dictionary, you have to use a specific syntax. And the spec notes that explicit prompt uses reverse Polish notation, or RPN.
Yes, RPN.
Now, for the listener who might not be a math historian or a hardcore systems programmer, can you explain RPN? Because it handles operations very differently from how we learn math in grade school.
Absolutely. The easiest way to understand RPN is to visualize a literal stack of objects. Imagine a spring-loaded stack of plates at a buffet restaurant.
Okay, oh God.
When you add a clean plate, it goes on the very top of the stack. When you take a plate off, you have to take it from the top. You can't just pull from the bottom without breaking all the plates.
Right, that would be a disaster.
In explicit prompt, data is stored on a memory stack exactly like that.
Okay, I've got the buffet plates in my head. Let's do some math with them.
All right, think about standard math. If you want to add 5 and 3, you write it as 5 plus 3. The operator, the plus sign, is stuck right in the middle.
Yeah, standard grade school stuff.
But in reverse Polish notation, the operator always goes at the end. The syntax rule is operand, operand, operation.
So instead of 5 plus 3, you would write 5 space 3 space plus.
Exactly. Here's what the kernel does step by step. First, it reads from left to right. It sees the 5. It pushes a 5 onto the top of the stack.
Okay, one plate down.
Next, it sees the 3. It pushes a 3 onto the stack. So now your stack has a 3 on top and a 5 sitting directly underneath it.
Ducking.
Finally, it sees the plus sign. Now, the plus operation is a command that tells the kernel, hey, take the top 2 items off the stack, add them together, and push the result back onto the stack.
So pops off the 3, pops off the 5, adds them to get 8, and puts a shiny new 8 right back on top of the stack.
You've got it. You're left with an 8. The beauty here is that there are no parentheses. There's no order of operations like PEMDAS that you have to memorize. No ambiguity whatsoever.
Fully linear.
Yes. The computer never has to guess what to calculate first. It just reads left to right, pushing data onto the stack and executing operations whenever it sees a command word.
And the spec outlines some of the basic built-in primitive words that manipulate this stack. Things like DUP, which I assume just duplicates whatever is currently on top of the stack.
Correct.
Or drop, which throws the top item away entirely.
Sure.
Or swap, which just flips the position of the top 2 items.
Those are your fundamental building blocks. And because of the dictionary we mentioned earlier, users can actually define their own new words using these primitives.
How does that look?
The syntax for that is a colon, the new word name, the operations, and a semicolon. So the spec gives a great example. Colon, ADDTDUO, the number 2, the plus sign, semicolon.
Okay, let me make sure I'm following this. If I define that, and later I type the word ADDTWO, the kernel will automatically push a 2 onto the stack, and then immediately execute the plus command on whatever was already sitting there.
Precisely.
So if I had a 10 on the stack and I typed ADDTWO, it pops the 2, pops the 10, and leaves a 12.
That's exactly how it works.
Okay, but I have to play devil's advocate here for a second.
Go for it.
You are telling me we are forcing fluid conversational AI through a 1970s calculator mechanism.
Right.
Doesn't that completely bottleneck the AI's creativity? I mean, natural language is messy and nuanced. This stack system is incredibly rigid.
If we connect this to the bigger picture, that strict, deterministic, stack-oriented operation is exactly the point. It is what keeps the AI system fast and prevents it from hallucinating,
Because it limits its options.
because it removes the ambiguity. If you just feed raw, messy English into a complex AI agent, it has to spend a massive amount of computational energy just trying to figure out what you want. It's essentially guessing. By using LPN and a strict stack, explicit prompt removes all the guesswork.
I see.
The operations are absolute. It either executes the stack perfectly or it fails explicitly. There is no gray area where it decides to, invent a chicken essay.
Uh-huh, right. That makes sense from an engineering standpoint. But the vision of this deep dive was to figure out how this code builds human rapport. Here's where it gets really interesting for me. How on earth do you get empathy out of a sterile stack of numbers?
Right, it seems contradictory. But it achieves this by forcing the AI to categorize and structure its output using VAK cues.
VAK.
Yes, VAK stands for visual, auditory, and kinesthetic. In NLP-1, therapists and communicators know that people naturally favor different sensory modalities when they talk.
Like how some people are really visual learners.
Exactly. Some people are highly visual. They say things like, I see what you mean, or let's look at the big picture. Others are auditory. They say, I hear you loud and clear, or that sounds good.
And kinesthetic would be touch.
Right. Kinesthetic or tactile. They say, I have a good feeling about this, or let's grasp this concept.
Okay, so explicit prompt builds these human modalities right into the syntax. The spec gives a really interesting example of this. It shows a line of code that reads V colon, quote, sunlit code grass, end quote, describe.
Yes, that V colon prefix is the crucial part. When the system processes that, the V colon tells the AI that this particular piece of data must be rendered visually for the user.
So it's not just returning text, it's returning visual text.
Right. It's instructing the system to generate a highly descriptive visual paragraph, or perhaps even trigger an external image generation protocol to show you a picture.
And if it were an A colon instead?
An A colon prefix would demand an auditory simulation. It would instruct the AI to emphasize tone, pitch, or pacing in the text, maybe use onomatopoeia, or even trigger a text-to-speech engine to read it aloud to you.
Oh, that's wild. And K colon.
A K colon prefix focuses on kinesthetic outcomes, so tactile, actionable steps the user can feel or interact with directly. By explicitly tagging data this way, the code forces the AI to be multimodal and psychologically aware of exactly how it's framing information to the user.
That is a really clever way to bridge the gap.
Yeah.
You're using mathematical stack operations to basically push a specific sensory framing onto the AI's output.
Exactly.
And that plays right into what the spec calls the agentic flow. Because like any programming language, explicit prompt has control structures. It borrows classic loops like do loop and conditionals like fills in.
Right, standard programming fare.
But it introduces NLP3 specific commands, specifically pace and lead. What do those actually do?
The pace-led flow is arguably the most powerful psychological tool in the language. Think of a hostage negotiator. They don't just walk into a room with a megaphone and yell, put the weapon down.
Right, that would be leading way too fast.
Exactly. The person would reject it immediately. Instead, they say, I can see you're upset. It's been a really long, stressful day. That's pacing. They are meeting the person where they are, validating their current state and context.
Building that baseline of trust.
Yes. And once that rapport is established, then they gently guide them toward a new state. Let's sit down and talk this out. That's leading.
So how does a computer replicate a hostage negotiator in code? That sounds impossible.
It does it structurally. The pace command forces the system to assess the user's immediate context using those NLP-1 cues we just talked about. It ensures the system's output mirrors the user's current situation. Then, the lead command guides the programmatic logic to the next outcome.
So it's 1-2 punch.
Exactly. Together, pace-led acts as a proactive control structure. Instead of the AI just passively waiting for the user to say something random, it is actively managing the interaction smoothly and confidently.
To really visualize this, I want to look at the real-world application mentioned in the source material, because it makes it so much clearer. It references a system called ChatQuest, the NLP3 adventure.
Oh, this is a great example.
Yeah, it's an AI-driven text game that runs on something called the game engine game loop for syntax realms. Now, text-based RPGs are notoriously difficult for AI to run consistently.
Because players are absolute agents of chaos. They can and will type literally anything into the prompt.
Let's do some role play here to test this. Imagine I'm playing ChatQuest. I want to be a difficult player. I type a messy, natural English sentence into the prompt. I say, I aggressively explore the spooky left path in Code Village Fork while whistling.
Ah, perfect.
How does the stack handle all that fluff?
Well, if you feed that raw sentence to a standard AI, it might decide to invent a whole new whistling mechanic for the game, or it gets distracted by the word spooky and turns the game into a horror story, entirely forgetting that you were standing in Code Village.
The runaway state.
Right. But in explicit prompt, the kernel pre-processes that sentence. It tokenizes the natural language and maps it to the dictionary. It looks for actionable commands it actually understands.
The spec actually shows exactly what that preprocessed translation looks like. It turns my messy English sentence into this clean stack. It reads location : quote, code a village fork, end quote. Then left path, then describe, then pace lead.
Notice what it did there. It completely stripped away aggressively and whistling because they aren't relevant to the core game loop, or perhaps they just aren't in the dictionary.
It just ignored them.
Yes, it pushed the specific location code village fork onto the stack. It pushed the action left path onto the stack, called the describe primitive. And most importantly, it capped the entire execution off with the pace lid command.
So it acknowledges where I am, describes the left path to pace me, and then immediately leads me to the next decision point so I don't get stuck whistling in the woods forever.
Precisely.
So what does this all mean? How does translating the prompt like this actually prevent the AI from crashing?
It prevents what the spec calls runaway states. As we noted earlier, a runaway state is when the AI loses the plot, it enters an infinite loop of generating text, or it radically breaks character. Explicit prompt stops this in a few distinct ways.
Okay.
First, mechanically, it enforces bounded loops and stack limits. If the stack gets too full of commands or a loop tries to run for too long, the kernel just stops it.
A hard stop.
Yes. But the real psychological and semantic safety net is the ontology.
Ah, the ontology. The spec mentions it builds on the Alien API ontology and ChatBot Brain's ABI top-down design. I know we love throwing acronyms around here, but what does that actually mean in practice?
Let's break it down. Think of Chatbot Brain's ABI, which in this context functions as a strict architectural blueprint for top-down design, like building a house.
Okay, building a house.
Instead of letting the AI build a house however it wants, ABI forces it to pour the foundation first, then build the walls, then put on the roof. It has to follow the order.
And the ontology.
An ontology is the dictionary of approved materials for that house. It's a predefined map of meanings. In explicit prompt, every single word must have an explicit, unambiguous definition in the ontology before the system proceeds.
The spec uses a really great example for this. Imagine a user in ChatQuest types the word bank.
Right, I want to go to the bank. Now, in a medieval fantasy game, they probably mean the grassy bank of a river.
Right.
But if they've somehow wandered into a cyberpunk city level, they might mean a financial institution. A standard AI language model might just guess based on probability, and suddenly your medieval knight is depositing gold coins into a modern ATM in the middle of a muddy river.
Which completely breaks the immersion. It's ridiculous.
Yeah.
So what does explicit prompt do instead of guessing?
It checks the word bank against its ontology. If it looks at the current game context and cannot definitively resolve, which meaning the user intends, it does not guess.
It just refuses.
It stops the execution. It throws an explicit error that says, quote, unresolved, meaning : bank.
It just halts the process entirely.
Yes. And that strict error handling is a feature. It is not a bug. By refusing to guess, it guarantees the game state remains stable and deterministic. It forces the system, or it prompts the user, to clarify before the AI generates a single word of response.
That makes so much sense.
Combined with the ABI blueprint philosophy, this ensures that the overarching narrative or the game loop never derails. You never end up with the chicken essay.
Wow. So to synthesize all of this for you listening at home, explicit prompt basically takes the chaos out of natural language. It forces all that messy human communication through a highly disciplined retro-style stack,
Yep.
and then it wraps the output back up in psychological communication techniques so the user still feels completely understood.
That is an excellent summary.
But the spec is also very transparent about its current limitations, right? It's not a magic bullet for everything.
No, it's not. Currently, explicit prompt is heavily focused on prompt preprocessing. It is not fully Turing complete on its own without extensions.
And for the listener, Turing complete essentially means a system can compute any mathematically possible problem given enough time and memory. So you couldn't build an entire operating system out of explicit prompt.
Exactly. You aren't building Windows 11 with it. Furthermore, it's designed to run in REPL environments.
RPL.
RPL stands for Read, Evaluate, Print Loop. It's basically an interactive, text-based command line. And crucially, it is designed to run with absolutely no internet dependencies. It operates entirely contained within its own local kernel and dictionary.
Right, which makes it incredibly secure and fast.
Hmm.
But looking at the future extensions mentioned in the sec, it gets really interesting. They talk about adding NLP2 machine learning integrations for more advanced dynamic parsing later on,
Yes, to make the dictionary smarter.
and expanding the dictionary for completely different domains, not just games like ChatQuest.
Right, the architecture allows for building entirely new ontologies. You could build one for finance or even biology. The spec specifically mentions integration tools like PullIP, which is a library for linear programming, often used in complex financial or logistical modeling,
Oh, wow.
or BioPython, which is used for parsing biological computation and bioinformatics.
That is wild. Imagine having a heavily structured, psychologically pacing AI helping you parse complex biological sequences or logistical supply chains without ever losing focus. You're getting the strict accuracy of a 1970s stack calculator delivered with the conversational empathy of a hostage negotiator.
It's an incredibly powerful synthesis. NLP3 in action.
And it leaves me with one final thought to ponder, because this raises a really interesting question.
Oh, what's that?
If explicit prompt can successfully boil down human rapport to a stack of basic primitives, if it can use NLP1 techniques to pace our mood, mirror our sensory modalities with VAK cues, and smoothly lead our actions just by popping commands off a stack, does that mean our own human conversations are basically just biological algorithms?
What?
Are we just pacing and leading each other, executing social code without realizing it? It really blurs the line between how machines process language and how we do.
That is the ultimate question when you start reverse engineering human communication like this. Are we the machine?
It's a lot to think about.
Yeah.
But that is all the time we have for today's exploration of Explicit Prompt. Thank you so much for joining us on this deep dive. Keep questioning the code, keep exploring the sources, and we'll catch you next time.